Good day, students. Welcome to Scholars Universal School Online. This is mathematics class. Today's topic is matrices. First, we'll be looking into introduction of matrices. We'll work on addition of matrices and subtraction of matrices. It simply means that at the end of this class, you should be able to know what a matrix is. You should be able to add two matrices together and should be able to subtract them as well. Remember that we care for you at Scholars Universal School, and kindly log on to our website and also subscribe to our YouTube channel. What is a matrix? A matrix is taken as or is defined as a rectangular array of numbers. When you say rectangular array of numbers, you see what it means soon. So you have rectangular array of numbers or other mathematical objects. It could be number, it could be any mathematical object, such as alphabets. But this subject, simple arithmetic operation can be performed on them. Arithmetic operations such as addition, subtraction, and multiplication as well can simply be performed on them. So let us look at the way matrices are arranged. Usually a matrix will have two areas. We have what we call the column, which just shows the vertical arrangement of number. Then you have what we call the horizontal arrangement of numbers also, which is simply known as the row. So we have the row, we have the column. So row points, this points to the direction, horizontal direction. So the row points to the horizontal direction of the arrangement of numbers in matrices, while this column is indicating the vertical arrangement of such numbers as well. Now, we can simply take a look at the general representation of a matrix. This is a simple 2 by 2 matrix, which we'll be calling a square matrix later. You see this, you have the row this way. Here now we have R1, C1 and R2, C2 as the row column number. So here you have the row here, then you have the column here. So in this row, you have a number which is at the point of meeting of the row 1, column 1 here. This is the row, this is the column. So here every number has the row which it belongs to, and it has the column which it belongs to, as you will see later. So here, this is column 1 and this is column 2. But this is row 1 and this is row 2. So let's go further by looking at some examples. So you have an array of numbers this way, where you have an array of numbers this way, where you have 8, 12, 16, 5. Please note that we use colors to differentiate the numbers so that you can know what it belongs to. Like 8 now is printed in blue. This is 8 here. So it means that this row, it is the one belonging to row 1, column 1. Then you have 12 belonging to row 1, column 2. That's the first row, but second column. Then you have 16 belonging to the first column here, but in the second row. So second row, first column, whereas 5 belongs to the second row and the second column. So we can go ahead to see that R1, C1 equals to 8. So any number here, R1, C1 equals to 8. R1, C2 equals to 12. Then R2, C1 equals to 16, and R2, C2 equals to 12. So here now, if we ask you which numbers belongs to row 1 here? 8 and 12 belongs to row 1. This is the row 1, this way. Then, which numbers belong to row 2? 16 and 12 belong to row 2. But if we now talk of column, column is the vertical. You view the number vertically. 8 and 16 belong to column 1. 12 and 5 belongs to column 2. I've told you earlier that every number has its own row and it has its own column. So here now, 8 belongs to row 1 in column 1. 12 belongs to row 1 but in column 2 because this is second column as indicated here. Then 16 belongs to second row. You know, this is the first row, this is the second row. So 16 belongs to the second row, but in the first column. That's why we say it is row 2, column 2, or column 1, sorry. Then when you look at 5, 5 belongs to row 2, column 2. So this is the second row, but in the second column. I hope you understand that. So you can also have matrices. You don't forget that you have just 2 here, 2 column, 2 row here. You can equally have things like this, where you have 3 column, column 1, column 2, column 3, and you have row 1, row 2, row 3. So this is simply called a 3 by 3 matrix. So let us take a look at the type of matrices we have. We have what we call a row matrix. When numbers are arranged in horizontal pattern or horizontal direction, we say the numbers are in row. But for column matrix, when we have the numbers arranged vertically in vertical direction, we say it is column. So we can have a matrix that is just one column. We can have a matrix that is just one row, no column. So when we have it like that, it's not as if they don't have row or they don't have column in either case. But what happens is that in the first case, the column there is not prominent, so we call it a row matrix. But in the second one, the row is not prominent and we call it a column matrix. So let us take a look at the square matrix here. Don't forget that we call this a square matrix because we have equal number of numbers at the row and equal number of numbers at the column. So where we have that, we also call this one. We have equal number of rows, equal number of columns. We have 1, 2, 3 numbers at the row. We have 1, 2, 3 numbers in every column. So once they are equal, once the row is equal to the column, then you call it a square matrix. Then you have what you call a rectangular matrix, and you have what you call identity of unit matrix. You also have what you call zero matrix. So let's proceed and look at this type of matrices. We have a row matrix here. You can see that this row matrix is only having one row like this. You cannot really identify the column because you cannot just say that, okay, is this the one number at the column. So although the column may be there, but it's not prominent and it is not valid. So we call it a row matrix because all numbers here are arranged in horizontal direction, which is the row. So for example, we can have a row matrix this way where you have 8, 11, 16 as the component of the matrix, or what we can call element of the matrix. Then we can also go further to see what we call column matrix, as we said earlier. Recall that I said column is the arrangement of numbers vertically. And don't forget that here we are using ABC to represent certain number. So we can have this. This is an example. For example, we can have this number arranged this way, 539. Just any number. You can arrange any number that way. When you arrange them that way, they become what? A column matrix. And if you arrange them in horizontal direction, they become a row matrix. Let's go further to now see what we call a 2 by 2 square matrix. So we have two elements in the row 1 here, 1, 2. Then if you look at it vertically also, 1, 2. So 2 here, 2 here. Since the number of numbers you have at the row is equal to the number of numbers you have at the column, so it becomes what we call a square matrix. Then we can have an example this way, that 2 by 2 matrix, where you have a 2 by 2 square matrix. Now I can choose any number. So I have decided to choose 7, 10, 19, 12, and I arrange them this way. Now it will be okay for you to choose your own number as well and arrange them either as a row matrix as we have done here, or as a column matrix as we have done here, or you choose numbers that you can arrange as square matrices. So we can also have what we call 3 by 2 rectangular matrices, where we have three rows: row 1, row 2, row 3. Row 1 is A and B, row 2 we have D and E, row 3 we have G and H. But we have column 1 and we have column 2. In column 1 we have A, D, G, and in column 2 here we have B, E, H. So it becomes a rectangular matrix because the number of the row is not equal to the column. So let us now talk of the identity matrices. We have what we call identity matrices. Let us see. Identity matrices is said to be a square matrix with 1 on the main diagonal and 0 everywhere else. It means that when you have a matrix like this, so it is a square matrix as we have been told. So when you have a square matrix of this nature that we have been talking about earlier, for example, let us say this is a square matrix. You have 1 here, you have 1 here, that's at the diagonal, but all other ones are 0. D and B are 0. Even if you have a 3 by 3 square matrix here, this 1, 2, 3, that's A, E, I at the diagonal. That means A will be 1, E will be 1, I will be 1, every other number will be 0. Then it becomes an identity matrix. So let us have an example here. So let us take a look at 2 by 2 identity matrix. Can you see that? You have 1 here, you have 1 here, and you have 0 in other places. So you call this a 2 by 2 identity matrices because you have 1 at the diagonal, 1 here, and 0 in all other places. So you can also have 3 by 3 identity matrices. Look at the diagonal here. 1, 2, 3. You have 1, 1. Every other number is 0. So these are typical identity matrices. We also call them unit matrices at times. So the identity matrix, they are identity because when you multiply them with their identical matrix, you will get back the same matrix. For example, if you multiply this matrix by itself, by the same matrix again, you know, if you multiply, let's say if you multiply 4 times 4, it's supposed to give you 16. But for identity matrix, it's not like that. If you multiply this by it again, that is 1, 0, 1, 0, you multiply it by another matrix with the same component, you will still get this matrix back. The same thing happens here. That's why we call them identity or unit matrix. We can also talk of zero matrix, whereby all components of the matrices or all elements of the matrix are 0. For example, you have 2 by 2 zero matrix. You see that there's nothing there. Every number there is 0. Then you have rectangular matrices, which is also 0 matrix. So you have 2 by 3 0 matrix here. Now we also have what we call zero matrix. And this is when all elements, all components of a matrix sum up to 0. That means if you have all components of matrix that result to 0, then you know that is a 0 matrix. For example, let us have this. You have what we call 2 by 2 0 matrix there. That means this 0 matrix is having 2 rows and 2 columns. That's column 1, column 2, row 1, row 2. Then you have what we call 2 by 3 rectangular 0 matrix. Call them 0 matrix, of course, you can see for sure that there are no other number there other than 0. For identical matrices, they are always identical matrices are always identity matrices are always square matrices with 1 at the diagonal and every other number is 0. But 0 matrices, no 1 at all, everything is 0. So let us now go to how we can add or subtract one matrix from the other. Don't forget that this in matrices we can perform addition, subtraction, and multiplication. So we are going into addition first, and there are two types of there are two ways. Okay, there are two things we consider here. We'll consider the addition first. In our first example, if A equals to a matrix with element 5, 2, 8, 1, then and B equals to a matrix with element 4, 7, 6, 3. What this tells us is that, okay, we are asked to find A plus B and we are asked to find B plus A. So when we see this A plus B, we are going to add just as our normal addition. First number here, that is first number, first row column here. So first number here, 5, will be added to first number here. The second number here will be added to the second number here. So 5 will be added to 4, 2 will be added to 7, 8 will be added to 6, 1 will be added to 3. And with that, you have performed the addition of matrices. So this is 5 plus 4. Then the next one will be 2 plus 7. So 2 plus 7. The next one will be 8 plus 6. You can see that. And the last one will be 1 plus 3. And we can proceed to having an answer which is equal to 5 plus 4 will give us 9, and 2 plus 7 will also give us 9 here, and this is 14, and 1 plus 3 will give us 4. So with that, we have added the matrix. So the matrix A here plus matrix B here equals to a matrix with elements 9, 9, 14, 4. We can also change the arrangement by considering number 2, that instead of having A plus B, then let us now have B plus A. If you have B plus A, will there be any change? So it means that we have to add 4 plus 5 now. 4 plus 5 and 7 plus 2 and 6 plus 8 and 3 plus 1. What do we have? We can see that this will still give us 9, 9. Then we'll have our 14 here, and we have our 4 as the last answer. So we can see here that there's no problem with the addition. A plus B equals to B plus A. And you remember in your matrices, remember in your, what do you call it? In the past, some of the topics you have treated in the past, when you perform addition and if A plus B equals to B plus A, what do you say it is? You say that A plus B are commutative under addition. So the same thing here, the matrix A plus B and B plus A are commutative under addition. So we can observe. What can we observe? What can you observe? So the answer to A plus B is equal to the answer to B plus A. So we can proceed. So we can conclude here that A plus B equals to B plus A. These matrices A and B are what? They are commutative under addition. If you say 2 plus 3 equals to 5, and you say 3 plus 2 equals to 5, then you say 3 and 2 are commutative under addition. So let us now go to example 2. So we'll be having a subtraction this time. In the first instance, we were able to have A plus B, and then we were able to confirm that A plus B is also equal to B plus A. But let us now consider another question here, where we have A equals to a matrix with element 5, 2, 8, 1, and B is a matrix with element 4, 7, 6, 3. How can we get this? We have been asked to find 1. A minus B. 2. B minus A. Let us see what happens here. So first we go to A minus B. And when we have it, it simply means that we'll be subtracting the element of B from all elements of A. So you have 5 minus 4. You have 2 minus 7. You have 8 minus 6, and you have 3, you have 1 minus 3. And that gives you 1 minus 5, 2, and minus 2. It therefore means that the answer to our question, A minus B, matrix A minus matrix B, will be equal to a matrix with element 1 minus 5, 2 minus 2. Then we can go further to find what the value of B minus A is. Here we have to be cognizant of the fact that the arrangement has changed. We are now having A being subtracted from B. It means that all elements of A will be here, but all elements of A here will be subtracted from the corresponding element of B. It means that 5 will be subtracted from 4, 2 will be subtracted from 7, and so on. So let us see, and let's see what happens, whether we still get the same value here just as we got for A plus B and B plus A. So B minus A gives us 4 minus 5. Second one, 7 minus 2, 6 minus 8, and 3 minus 1. And that gives us minus 1. That's 4 minus 5. 4 minus 5 here equals to minus 1. 7 minus 2 will give us 5. 6 minus 8 will give us minus 2 here. And 3 minus 1 will give us 2. You can see that there's a change here. The first number here is 1. This one is minus 1. The second number here is minus 5. This one is 5. The third number here is 2, and this one is minus 2. And the fourth number here is minus 2, and this one is 2. So here, it means that A and B they don't behave the same way under subtraction. They behave the same way under addition, but they don't behave the same way under subtraction. So we now say that A and B are not commutative under subtraction. That is our observation. So what can you observe? You observe that A minus B is not equal to B minus A. And from what you have here, you will see that for each value here, you have the negative form of it. Each value here, you have the negative form of it. Each value here, you have the negative form of it. Each value here, you have the negative form of it. It simply means that B minus A equals to minus into bracket A minus B. So we have it here, A minus B equals to minus into bracket B minus A. So A minus B is not equal to B minus A. These matrices A and B are not commutative under subtraction. They are not commutative because we are unable to get the same answer. So this is how far we can go today. We want you to solve this as a class exercise that will show that for the above matrices A equals to 2, 3, 4, 2 and B equals to 3 minus 1, 1, 3. Show that matrices A and B are commutative under addition but not commutative under subtraction. Thank you for learning with us at Scholars Universal School Online. Remember to subscribe to our YouTube channel and our website. As you can see there, you subscribe free to our YouTube channel. Remain blessed and have a wonderful time.